Okay, we're starting here on 4.8, which is L'Hôpital's rule. L'Hôpital, Guillaume L'Hôpital, was a French mathematician, and he's credited with this tool that is, you'll soon find out, is very handy for finding limits and things like that. However, he didn't actually find it. It got his name, but it was actually his teacher was the one that came up with it. And his name is Bernoulli. You guys know Bernoulli, I'm sure, who was also Leonard Euler's teacher too. So this guy taught these two here. So he was pretty impressive. But first, before we learn about the rule, we need to talk about one term, and it's called an indeterminate form. So an indeterminate form takes on a couple different looks. The L'Hôpital's rule only works when we have either a 0 over 0 as a limit or infinity over infinity. And this can be negative or positive infinity. But the point is there's an infinity over infinity. It works in this kind of a rational form here, in a fraction form. However, there are other indeterminate forms. For example, 0 times infinity is an indeterminate form. Infinity minus infinity is an indeterminate form. 1 to the infinity power is indeterminate. Infinity to the 0 power is indeterminate. 0 to the 0 power is also indeterminate. So when you get these forms, and I'll show you some examples of these, my friends, you need to convert them to this form, to a fraction, a rational expression, in order to use L'Hôpital's rule. You cannot apply it like this. So if you get one of these indeterminate forms and you can't use it, then you can't use, when I say you can't use it, I mean that you can't convert it into a rational expression, then you can't use L'Hôpital's rule. L'Hôpital's rule is super cool, very, very, very handy. I will give you a word of warning. When you have these here, you're going to have to, well, you're not going to have to, but you may have to do some tricky algebra to get this into one of these forms. So let's begin. So the rule is simply, and it's very easy, my friends, it's if you have a limit of x going to some value a of a function over another function, and that answer, when you take the limit, is 0 over 0, you can then take the derivative of the numerator and the denominator separately. This is not the quotient rule. You simply take the derivative of the numerator and leave it, take the derivative of the denominator and reevaluate it. And hopefully when you reevaluate, you're going to get an answer. If you don't, if it's still 0 over 0, you can do the process again. You can use L'Hôpital's rule as many times as you'd like. So here's our classic example. What's the limit as x goes to 0 of sine x over x? You remember that from when we were very first doing limits. We already know the answer is 1, but let's just check it. When I put 0 in here, when I insert 0 into the equation, notice I get that 0 over 0, which is the classic indeterminate form. So using L'Hôpital's rule, I'm going to go ahead and take the derivative of the numerator. The derivative of the sine is the cosine. Take the derivative of the denominator. The derivative of x is 1. And so here's that derivative of the numerator, derivative of the denominator. Recompute that limit. So the limit as x goes to 0. Well, the cosine of 0 is 1, and the limit as x goes to 0 of 1 is 1, so the answer is 1, which you already knew. We knew that from before. So let's practice. Let's see how this works. So here's 4 different problems. Remember, the step 1 is always to make sure you get the indeterminate form. If you don't, then you have your answer, right? If you get an infinity, or you get 0, or you get a number, those are, you don't need to use L'Hôpital's rule. So I have 1 minus the cosine of x over x. As x goes to 0, I get 0 over 0. Take the derivative of this. Derivative of 1 minus cosine x is sine x. Derivative of x is 1. 0 over 1 is 0. And the next problem is the limit as x goes to 1 of sine of pi x over ln of x. That's a 0 over 0. Taking the derivative, well, this is the chain rule, so I get pi cosine pi x over 1 over x. And you're going to get a lot of these where there's some kind of a fraction. Remember to use your algebra rules. You can flip that around. You can leave it where it is. If you can evaluate it, you can move it to the denominator or numerator, whatever's appropriate. In this case, we don't need to worry about it because we're going to 1. So 1 over 1 is just 1, so we don't have to fiddle with that. Pi times cosine of 180 is negative 1, so the answer is negative pi. Down here, this one's getting a little tricky. We've got e to the 1 over x minus 1 over 1 over x. This is the limit as x goes to infinity. So this would be 1 minus 1, so that's 0, because e to the 0 is 1, right? And 1 over infinity is also a very tiny number, which is 0. So now we have to evaluate this. Well, this is chain rule. So this is e to the u du. So there's my e to the u. The derivative of 1 over x is negative 1 over x squared. And then the derivative of 1 over x is negative 1 over x squared. Now, in this case, you can see, oh my goodness, this is looking ugly. But wait, these are the same thing. So these just cancel. And so we recompute what's the limit as x goes to infinity of e to the 1 over x. And that is e to the 0, and that's basically 1. And last one, here's another one, sine x minus x over x squared. We compute that, and here's one where we have to do it twice. So when I get my first version, my first iteration of L'Hopital's rule, I get, this is going to be 1 minus 1, that's still 0 in the numerator, and 2x, that's still 0 in the denominator. So we do it again. Derivative of cosine x minus 1 is negative sine x. Derivative of 2x is 2. Now I have a number down here, so I don't have to worry about doing it again. And then that's 0 over 2, which is 0. And we said, so those are the 0 over 0 forms. We said we can also have the infinity over infinity forms. So that's these cases here. And I think you're going to see that when we were talking about end behaviors of functions, you see, remember this, the limit, what's the end behavior of this function? Remember we said, oh, it's just the ratio of the coefficients if they're the same, if the powers, or I mean, if the degree is the same. Well, look, that's because of L'Hopital's rule. So this is infinity over infinity. So I take L'Hopital's rule. Well, this is 3 over 2, and the answer is 3 halves, which you already knew. The end behavior of this function as x goes to infinity is 3 halves. Here's another one. This is as we approach 0 from the right of the ln, because we can't take ln of a negative number, so we have to approach from the right. So that's negative infinity. And then the cotangent is also in infinite. In that case, it's heading to infinity. There's asymptotes there. So that doesn't work. So then we take the derivative. The derivative of the ln of x is 1 over x. And the derivative of the cotangent is the negative cosecant squared. This is still infinity over infinity, so this isn't helping. However, I can see here that I can work with this. 1 over x means I can push this x down into the denominator, and cosecant is 1 over the sine. So I can push this into the numerator. So now I have sine squared x in the numerator, and x in the bottom. Now, I brought the negative up here, but I'm just going to put it down here with the x. I'm just going to move it down there so that when because we have to do the chain rule here, and I'd like to keep that negative out of there just to keep it simple. So then here we are. And again, notice I still get 0 over 0, no help. So we compute. So the derivative of the sine squared x is going to be 2 sine x cosine x. That's chain rule because this is u squared. Right? U squared, the derivative of u squared is 2u du, 2u du, right there. And then the derivative of negative x is just negative 1. So as soon as you see there's a number down here, you know you don't have to do it anymore because you're going to get an answer. And 2 times sine x cosine x as x goes to 0. Well, the sine of 0 is 0, so then this whole thing is 0. So 0 over negative 1 is 0. So these are a little trickier here. And then more tricky ones are when we get these other kinds here. So let's look at a 0 times infinity. So here we have x ln x. We need to rewrite this, right? Because we can't use L'Hopital's rule in this form. So in this case, I'm going to write this as ln x over 1 over x. I'm going to take the reciprocal of x there. And then now compute, and I surely get this, like, because we already knew that, right? So negative infinity over infinity. Take the derivative of both, 1 over x, negative 1 over x squared. You see I can do a double flip. So this x pushes down, this x pushes up. So it's negative x squared over x, which is just negative x, and that would be 0. So some algebra work to do there. So if we're not comfortable with that, we might have to sit there with a little bit on those. Here is an infinity minus infinity. So when you get these, I think you know most of the time you're going to have to just find a common denominator to turn it into one fraction. So I have limit as x goes to positive infinity of 1 over x squared minus 1 over tan x. That's infinity minus infinity. So then I just make a common denominator. So I get tan x minus x squared over x squared tan x. And then from here, I recompute, and it's still 0 over 0. All right, take the derivative. Well, the derivative of the tangent is the secant squared. Derivative of x squared is 2x. So there's my numerator. Denominator, it looks like I need to do the product rule. So I've got u dv plus v du. I just put the 2x in front, so I didn't have to use parentheses. And so now let's see where we are. Secant of 0 is 1 minus 0, so I have a number in the denominator, in the numerator, so I'm good there. And down here I have, well, this term is 0 and that term is 0, so I have 1 over 0, which is okay because that just means infinity, right? So this is going to positive infinity. And let's see. Oh, this is a good one. This is tricky. This is really tricky. This is infinity to the 0 power. So this one, we're going to have to earn our pay on this one. So step 1 is we evaluate this, and then we're like, okay, well, there's no way to turn that into a rational expression yet. So what I'm going to do, though, is I don't like this. So I'm going to take the ln of both sides. So remember doing that logarithmic differentiation. So we're going to do that technique here. And so I'm going to take the ln of y, and I put a square around here because we need to come back to this at the end of the problem. So the left side, just put a pin in this here. We need to come back to this. So the ln of y equals the ln of x to the 1 over x. Well, you know that this pulls this down front. So I have 1 over x times ln of x. Well, now I can turn that into a fraction. Okay, now we can use L'Hopital's rule. So the limit as x goes to infinity over 1 over x is definitely infinity over infinity. Take the derivative, I get 1 over x over 1, which is 1 over x, which is 0. Okay, so that's the limit as y goes to infinity. But we took the ln of y. So really what we're doing is we're saying I'm taking the ln of the limit as x goes to infinity of y, right? Because we left this unchanged. We were just looking at y here. This is y, right? So we found that limit, but now we have to say that limit is 0, but what's the ln of 0? What's the ln of that limit? And that answer is 1. So that is pretty tricky, my friends. So usually, like I said, when we get to these, you're going to have to really do some hunting to find out what we need to do. So that's L'Hopital's rule.